Hello students, this is a recording on how to do the project slides that we should be able to complete by this point. So taking a look here at this point, we should be able to complete up to slide 27 of our project. So taking a look here, we've already completed the 3A notes, the 3B notes, and the 3C notes. So we're going to go ahead and start back here at slide 6, which is where you choose your metal element for your project. Taking a look here, you're only allowed to choose these 3 elements: sodium, magnesium, or aluminum. They're boxed in red. So you need to go ahead and type right here which one you chose. Now for my example, I'm not going to use any of these metals just because I don't want you to copy what I'm doing. So I'm going to go ahead and do an example, so please don't copy my example. But the example I'm going to actually use is going to be potassium. So I'll go ahead and right here, I will use, I'm going to use calcium. I'm going to go ahead and use calcium as mine, and this is example. Again, do not copy, because obviously that's not one of the options that you can choose. Right, so that's going to be my example right there. And then what I need to do is I need to go ahead and I need to indicate the number of protons that are in calcium. Now the number of protons again is going to come from the atomic number. So atomic number is the number that you see on the top of the element square. Let me go ahead and move this for a moment. So taking a look at calcium, you can see calcium, the top of its square says 20. Okay, so for me, I again would put 20 as my example. Okay, so that's the number of protons that my calcium has. So for you, if you're taking a look at sodium, again, your numbers that you're looking at are up here. So sodium, magnesium, aluminum, right there. Okay, so then what you're going to go ahead and do is determine the number of total electrons when the atom is neutral. Remember that you do need to have equal electrons and protons when neutral so that they cancel each other out, right? So for example, if we have, let me get it right here, if we have 3 protons, then each proton needs to be balanced or canceled by an electron. So then I would also need 3 electrons to cancel this out in order to equal a charge of 0, right, which is neutral. All right, so in that case, what I'm going to go ahead and do is I'm going to make sure that this number that I choose right here is actually equal to the number that I chose up here. So if I have 20 protons, then I should also have 20 electrons when neutral. All right, so 20 would be my example here. Okay, now let's go ahead. That's the total number of electrons. The next question, though, is asking about specifically the number of valence electrons, which is only the outermost electrons. Remember, if we take a look at, for example, I'll go ahead and show you the Bohr model of calcium. All right, so if we take a look at the Bohr model of calcium, we can see that we have all of these, right, 20 electrons. If you counted these up, you would see 20 electrons, but we're only going to be looking at the outermost ring. All right, so we're going to ignore everything on the inside, and we only want to know what's on the outermost ring. Now you could look up the Bohr model of your element if that's easier for you to understand, but really you only need to actually look at the group number. Remember that taking a look here, group 1 has 1 valence electron, group 2 has 2, and all the way down here, group 13, remember you only look at the last number, it actually has 3 valence electrons. So in my instance here, I'm taking a look at calcium. Calcium is in group 2, and so it has 2 valence electrons. Just like my Bohr model right here showed, you can see I have 1, 2, only 2 on the outermost shell, so 2 valence electrons. All right, so I would go ahead and type that here, 2 valence electrons. That's my example. Okay, again, it just depends on what group you are in, which is the column, the top number right here. Okay, and those notes are right here for you, so I'm not trying to trick you with that. All that information is right there. How many valence electrons does this metal want to then lose to drop down to an already full shell? So going back to this Bohr model here, let me go ahead and erase this so it's out of the way. Oops, sorry. I erased too many things. There we go. All right, let's go ahead and erase this stuff right here. Okay, so going back to our Bohr model, remember that the valence shell right here wants to have 8 valence electrons. So atoms will either try to gain electrons to get to a valence shell of 8, or they'll try to lose electrons to drop down to a shell like this one that's already full. In this case, calcium has 2 valence electrons, and remember, a full shell is 8 valence electrons. So you need to think to yourself, is it going to be easier to lose 2 or to gain 6? Go ahead, think to yourself. So in this case, it's going to be a lot easier to lose 2. So we're not going to try to gain 6 to try to fill up our current shell. Instead, we're just going to try to lose these 2 right here. And when those 2 are gone, you'll see that now we drop down to this shell right here, and this shell is already full. And this is true of metals. Metals will actually lose their electrons, which is why I already specified it in the description here that I specify it has to lose those electrons. So if you have 2 valence electrons and metals lose them, then right here, that's easy to say. You would just say that you need to lose 2 electrons. So right here, 2 electrons for my example. Okay, so that should be pretty easy to understand. Again, the number of protons is going to be equal to the number of electrons. The valence electrons, based on your group numbers up here, are actually also going to be the same number of valence electrons that you lose because they are metals. All right, make sure you pause the video, make sure you fill that out, and then continue on to your next element. Again, making sure that you only choose sodium, magnesium, or aluminum. Do not use my example. All right, so let's go ahead and talk a little bit about the nonmetal. So very similar process here, but this part, the valence electrons, are going to look a little bit different. So you need to choose your nonmetal element. You can choose nitrogen, phosphorus, oxygen, sulfur, fluorine, or chlorine. I'm going to actually go ahead and choose bromine down here just because I'm doing an example. All right, so taking a look here, my nonmetal element is going to be bromine. This is an example. Do not copy. Okay, so let me make that a little bit bigger and move that over here. Cool. Okay, so my number of protons, again, is related to the atomic number, which is at the top of the element square, right? So for you all, you'll be looking at these numbers for your protons right here. And for me, taking a look at bromine, it's a little bit hidden, but I know that this number right here at the top is going to actually be 35. So I'm going to go ahead and do 35 for my example, 35 protons. That's my example, okay? And then again, taking a look at the number of electrons, total electrons needed to keep this neutral, again, you need equal amounts. Our example was, let's go ahead and say if we have 4 protons this time, to cancel each of those protons out, we would need an electron to balance those and make it neutral. So I would also need 4 electrons. So in the same way, obviously we have more than 4 protons, but we can go ahead and say that since we have 35 protons, to cancel or balance it out, I would need an equal amount of electrons, and so I would need 35 electrons. So again, those 2 numbers should be equal to each other. I'll go ahead and just draw a reminder for that there. Okay, so the number of valence electrons, again, is the outermost electron. So once more, I could look up the Bohr model of bromine this time. Okay, and let's go ahead and take a look at the Bohr model of bromine. And I'm going to erase this information right here so it's not in my way. Oops. Here we go. Here we go. Okay, so let's take a look at the Bohr model of bromine. Again, bromine, I'm looking at the outermost shell for its valence electrons, so ignore everything in the center. All right, we're only looking at the outermost shell, which I can see has 1, 2, 3, 4, 5, 6, and 7 valence electrons. But again, I don't have to do that. I can actually just look at the family numbers, so I'll explain that part right here. So again, taking a look here, group 15. Again, remember, we only look at the last number. So group 15 actually has 5 valence electrons. Group 16, everything in group 16, oxygen, sulfur, selenium, is going to have 6 valence electrons. And then group 17, which is what bromine is in, bromine's in group 17, has 7 valence electrons. So again, I did not have to look at the Bohr model. I could have just done it this way. And in fact, let me go ahead and just box it like this so that we can really see it really well. Right here. Let me go ahead and box this for us and make sure that this is nice and thin for us. There we go. So again, here's, oops, that's too thin. Here's group 15. here's group 16, and here's group 17. So that should help you determine the number of valence electrons. Again, for me, bromine is in group 17, so for my example, I'm going to have 7 valence electrons. That's my example. Okay, so I have that there. All right, so this time it asks how many valence electrons does this nonmetal want to gain to get to a full shell. Remember, we want a perfect octet. Octet, again, meaning that we want to get to 8 valence electrons. We want 8 valence electrons in total on our outermost shell. Okay, so let's go ahead, let's explain this again using our Bohr model, just so that we can see it really well. So taking a look at our Bohr model right here, again, we're only looking at the outermost shell. Our outermost shell currently has 7 valence electrons, so you want to think to yourself, is it going to be easier to lose all 7 of them and drop down to a shell that's already full, right, this one? Or is it easier to gain 1? Think about that answer to yourself while I finish this up. And it's going to be a lot easier to just gain 1. We don't want to lose 7. That requires a lot of energy to try to lose 7 electrons. Instead, we just want to gain 1 electron, specifically right here, and that will get us to our 8. Okay, so I'm going to go back over here and explain exactly what that looks like. All right, so again, what we're going to do is we want 8 in total. And we already have 7. So to figure out what's left over, you need to subtract. So I would do 8 minus 7, and that would give me 1 more valence electron that I would need. If you are in group 16, then you need to do 8 minus 6, and that would mean that you need 2 valence electrons to gain. And if you are in group 15, that means that you currently have 5 valence electrons. Getting rid of those 5, you need 3 more to get to 8. All right, so that should help you out with that. I'm going to go ahead and erase that for now. Again, it's just subtraction. Take your 8, subtract what you have, and that will tell you what else you need. And so for my example, I need 1 more. Okay, so in this case, these are not the same like they were with our metal. Instead, when you add these together, they should add up to 8. Okay, so when you add up your valence electrons and what you need to gain, it should add up to 8 because that is our octet rule. Okay, so that's just a helpful hint. 7 plus 1 would equal 8. Perfect. So go ahead, pause the video, and complete slide number 7. All right, so now we're going to go ahead and move on to slide number 14, where we talked about the story for the ionic bonds. So we want to tell a story to explain to a child how a nonmetal and a metal form an ionic bond. So you're going to say, who are your metal and nonmetal characters? So make sure that you do include their actual names, so aluminum and fluorine, for example, but then also give them some fun first names like you see here. Please do not copy this example. Please do not copy the teacher examples here. That is called plagiarism, which is cheating. Okay, so please do not copy my examples. Explain how they're opposites. So for example, let's say one is happy and one is sad. Specifically, remember that in ionic bonds, the metals, all right, so this is our sodium, metals actually give something to the chlorine. So in this case, my example was one of these is happy, one of these is sad, and then we give something to the sad one. So in this case, it would make more sense for the chlorine to be the sad one. So I would actually make the metal the happy one, and the non-metal the sad one. Okay, the one that's getting something should be the non-metal. Okay, so I'll write that note here. The one who is getting something is the non-metal. So keep that in mind when you come up with your opposite characteristics. Okay, so my non-metal is going to be the sad one, and the non-metal for me this time is fluorine, right? So I would say fluorine, right, is sad. Okay, whereas my aluminum, my metal, is happy. Okay, so then I'm going to explain how my metal gives my non-metal character something. So I would say my metal gave the non-metal some cookies, right? So that was my example, and now they're both happy, right? Our metal is happy because he was already happy. Our non-metal encountered our sad non-metal, gave him some cookies. Now they're both happy, and this is just like an ionic bond. Again, taking a look at ionic bonds. metals have electrons that they want to give away. Non-metals have electrons that they want to gain, and so by exchanging those, everybody is now happy. Okay, so let's go ahead and take a look here at the sentence framing here. So you can use these sentence structures. Feel free to use them exactly how you see them. If you don't want to use these, you can also go ahead and delete all of it if you would like to. You don't have to use my sentence framing. Just make sure that if you do write your own story, that your story fits these 5 criteria right here. Okay, so taking a look here, once upon a time, for example, there was a metal named, all right, so for my example, in the example I said my metal was Tommy Aluminum, who was happy, right, was happy. There was also a non-metal named Sally Fluorine, who was the opposite, which was sad. All right, so again, do not copy my example. Okay, so then Tommy Aluminum gave cookies to Sally Fluorine. And from then on, they were best friends because now Sally Fluorine was happy too. Okay, so that would be my reasoning. Simple reasoning, right? Then you explain this is just like an ionic bond where metals, again, taking a look back over here, we should know that metals only have a few electrons. And so metals actually do want to give away electrons. I think that's right here, okay? So let me go ahead and I'll clear this out right now. All right, so metals, again, are going to lose or give away electrons. So this is going to be helpful with this. Okay, so taking a look here, right, so metal, you should be able to say gives or takes. Is it losing or gaining? Right, another way to think about it is lose/gain. Okay, and the non-metal, again, same thing. Does it lose or gain? Lose or gain. Again, all that information is right here in your notes on slide. What slide did I just have this on? On slide 3B, or on slide 10, okay? So tend to be nonmetals that have most of their valence electrons and want to gain a few more. And then based on that, right, what kind of charges do they become? So the metal, does it become positive or negative? Again, think about if it's losing electrons, then it loses negativity, and so it should become overall positive. If it gains electrons, it becomes more negative, making it negatively charged. Same thing with our nonmetal. If it loses electrons, it's losing negativity, becomes overall positive. If it gains electrons, it's gaining negativity, becomes overall negative. And they should end up being opposites, all right? So these should be opposites. If they're not opposites, then this would not result in a bond. Now again, the answers are all here on slide 10. So it actually tells you what metals turn into. So it tells you that metals turn into cations, nonmetals turn into anions, and in our notes we already filled this in. We explained cations, are they positive or negative, and anions, are they positive or negative. So again, all the answers are on slide 10 for this summary right here. I'll go ahead and just write that right here. So all the answers for the last bullet point are on slide number 10. All right, pause the video, go ahead and fill out your story or write your own story, and then continue playing when you're ready. All right, so let's go ahead and talk about how to analyze chapter 1. So we want to know what is your metal, what is your nonmetal, how many atoms of your metal and nonmetal do you need to balance the charges, and then what would be the final chemical formula. Okay, so let's go ahead and talk about this. I'm going to go back to the examples that I used, which were my metal was what did I say? Calcium. Calcium. And so do not copy. This is just an example. Okay. Again, you can't even choose calcium, so you shouldn't have calcium here. And my nonmetal, again, example was bromine. Again, do not copy. This is just an example. And so going back to that, right, for yours should actually be what was in your story. I know it was a little weird because I did fluorine and I did aluminum, but I should have done bromine and calcium based on what I chose, but I just wanted to keep consistent with the example I showed you. So anyway, so here's calcium, here's bromine. How many valence electrons did my metal want to use? Again, the answer here was on slide 6, slide 7. Slide 6, slide 6, and so I said calcium wants to lose 2 valence electrons. I already did that. All right, so this is all from, all from slide number 6. Okay, so mine wanted to lose 2. That was my example. And then, so what would my final charge be? So again, if you're losing 2 electrons, that means you're using 2 units of negativity. And so overall, you should become positive, right? So if you lose 2 electrons, you should actually become a positive 2 charge. Positive 2 because you actually lost negativity. You lost 2 negativity, okay? So then let's go ahead and take a look here. What is your nonmetal? Again, I said mine was bromine, and all of these are from slide number 7. How many electrons did, valence electrons did my nonmetal want to gain? Again, bromine was in group 17, has 7 valence electrons, just needs to gain 1 more to get to a full shell. So it wants to gain 1, and in this case, if we're gaining negativity, right, gain negativity, then overall we should become negatively charged. So I gain 1 negativity, so I should become -1 charge, right? So if you, however many electrons you lose, that's how much you become positive. However many electrons you gain, that is what you become negative for your nonmetal, okay? So that should be easy peasy right there. So then what we need to do is we need to think about how many atoms of your metal and nonmetal would you need to balance the charges, okay? So this one's a little bit more complex. This is not something that we went over explicitly during class, but let's go ahead and talk about this. So again, my calcium has a positive 2 charge, that's my metal, and my nonmetal has a -1 charge. And what I want to do is I want to get these to the same amount, all right? So I'm going to go ahead and try this out. I'm going to say, let's multiply them both by 1, or let me go ahead and, I'm going to start with the one that I have less of. So start with what you have less of. Okay, so I have less of the negative charge, so I'm going to go ahead and start off by multiplying that by the next number. So instead of multiplying it by 1, which would still give me -1, I'm going to go ahead and try multiplying it by 2. So times 2 of the atoms, 2 atoms. And then what does that end up giving me? That ends up giving me a -2 charge. And so do those balance out? Yes, right? So this first one, I didn't need to multiply. This is just 1 atom. All right, so 1 atom of it. So this one, I just need 1 metal atom, and down here, I would actually need 2 of the negative atoms, okay, to balance these off. Let me go ahead and give you some other examples here. All right, so let's say that you have a metal that has a charge of +1 and a nonmetal that has a charge of -1. Well, in that case, they're already balanced, so you only need 1 atom of each, right? So in this instance, I would only need 1 atom of each, right? So I would need 1 and 1, okay? Now let's say, for example, that I had instead a nonmetal with a charge of -3, okay? So in this case, I'm going to start off with what I have less of, which is I have less of the positive charge. So I'll go ahead and multiply that by 2 atoms. 2 atoms. And what do I get? I get a charge of +2. Well, that's not enough, so I'm going to go ahead and try again, and instead I'm going to go ahead and multiply it by 3 atoms. So I'm going to go, I'm going to go ahead and start just increasing that number, so I'm going to multiply it by 3 atoms this time. And now, +1 times 3 atoms would give me a charge of +3, which is correct. So taking a look here, in this instance, I would need 1 of the nonmetals, because again, I didn't need to multiply that. That's the same as saying multiplied by 1 atom. And on the top one, I would need 3 atoms, 3 of the metal atoms to balance it off, okay? And then let's go ahead and try one more example. This is probably the hardest. If for some reason you have a 2 and a 3 charge, so let's say we have a +2 charge and a -3 charge, and if yours is the opposite, it's still the same process. Start with what you have less of. So I would go ahead and I would multiply this by 2 atoms. 2 atoms, okay? And that would give me a charge of +4. So now I need to go to what I have less of, Okay, and again, what I have less of now is the -3 charge, so I'm going to go ahead and actually multiply that one as well. So multiply that by 2 atoms, and now I have a charge of -6. And now again, going back to what I have less of, now I have less of this +4 charge. So I'm going to actually go ahead and try to multiply this by a bigger number. Okay, so instead of multiplying it, instead of trying to multiply it by 2, I'll go ahead and try to multiply it by 3 atoms. And so that would give me a charge of +6, and now they're equal. So in this instance, I would actually need 3 of the metals and 2 of the nonmetals. Okay, basically just remember whatever you put in here, you should multiply it by the charge, right? So you would multiply it by this charge, this one you would multiply it by this charge, and those charges should end up being the same amount but opposite, right? So 3 times +2 would give me a +6 charge. 2 times in this case, I said that this was -3. So 2 times -3 would then give me a -6 charge, right, in this example right here specifically. And so that would balance off. Okay, so again, just think to yourself, whatever I'm multiplying my number of metal ions by, the positive charge, should then equal whatever I multiply my non-metal atoms by, their negative charge. Okay, so then we can go ahead and write the final formula here. Okay, so again, going back to what I originally had, I originally needed 1 metal and 2 nonmetals, because 1 times +2 would give me +2, and 2 times -1 would give me -2, and that balances off. So now I need to know the final chemical compound. In the final chemical formula, I'm going to start off by writing the metal first, which is the calcium. The abbreviation for calcium, again, is Ca, so write your abbreviation. Again, that comes from the periodic table, so NaMgAl. First letter capitalized, second letter lowercase. And the metal, I only need 1 atom of it, so I actually don't need a subscript. All right, so here, okay, remember that we said in class, no subscript is 1. Okay, so I don't actually need to put a subscript there. So Ca, and then I would go ahead and put that my B here is going to be my nonmetal, which was my bromine. So again, I'll go ahead and write my next one. So Br. And this time for my bromine, I said I needed 2 of my bromines. So I put a lowercase 2, okay? And these are already here for you, so you can just type it in. So just replace the A, highlight the A, and I would replace it with Ca. I would delete the X because I don't need a subscript. I would highlight the B and write Br, and highlight the Y and write 2. If for some reason you don't want to deal with the subscripts, you could just write it all out. I'll still understand what it means. Okay, so that's how we go ahead and do that one. Go ahead, pause the video, try that out. I know this right side is kind of the hardest one to do, so if you do need help on that, make sure you reach out to your teachers. Pause the video and continue playing when you're ready. Okay, so let's go ahead and talk about Chapter 2. So Chapter 2, we're going to explain how a nonmetal meets its identical nonmetal and forms a nonpolar covalent bond. So let's go ahead and I'll actually use my example. So instead of saying ace fluorine and pace fluorine, I'll use ace bromine and pace bromine. Not a big deal. It's still going to be very similar. So this is example. Sorry, I'll go ahead and write it over here. Remember, do not copy the teacher's example, okay? That are in the parentheses here. So I'm going to say, who are my 2 nonmetal characters? Again, make sure you include their actual elements, so bromine and bromine, but give them different names. You'll notice I named them similar because I want to emphasize the fact that they're very similar to each other. So how are the 2 metals identical? So in my example, they both love chocolate. And then because of this, they love it equally, and so they can actually share it equally. So they share a chocolate bar equally. And this results in friendship. Again, very simple reason, because now they're both happy. And again, this is going to be just like a nonpolar covalent bond that we learned in class. We learned for nonpolar covalent bonds, there's no difference in electronegativity between the atoms, and so our electrons have to be equally shared, like a tug of war where nobody's stronger. And so this happens in hydrogen, H2, nitrogen, N2, carbon, C2, and so on and so forth. Okay, so let's go ahead and take a look here. at my story again. Here we go. All right, so let's go ahead and actually take a look at the sentence structure here. Again, you can feel free to delete this and change it into your own as long as it meets these 5 criteria. I'm totally fine with that. But let me go ahead and actually show you how I would use it. So there was a nonmetal named ace bromine who was a chocolate lover. There was another nonmetal named pace bromine who was also a chocolate lover, okay? Because they are so alike, ace bromine and pace bromine love to share chocolate bars. They were so good at sharing fairly that they became best friends. This is just like a nonpolar covalent bond when 2 identical nonmetals share electrons equally or unequally. Again, you'll need to delete the wrong term there, and we should already know this. We just mentioned that in nonpolar covalent bonds, there is equal sharing. All right, so the answer here for us is on slide 19. So right here, this is on slide number 19. Perfect, okay? And let's go ahead and keep on moving here. So then we're going to go ahead and take a look at 27. So what is your nonmetal? Again, for me, my nonmetal here was bromine. And I'm going to go ahead and I'm going to draw 2 identical atoms of my nonmetal, draw the Lewis dot diagrams. So step 1, each atom by itself. Step 2, how the electrons get shared. And step 3, the resulting bond. This is something that you want to do on a piece of paper. You can try to use the scribble tool here, but I don't really recommend it. It's going to be really hard to do it for easily. So I really recommend write it onto a piece of paper, and then if you're doing it on a piece of paper, you have to make sure your name is next to the diagrams. So make sure to handwrite your name on it before taking the picture so I know it's your genuine work. Okay, this is actually one that we did in class. Again, we showed you in class that bromine right here is a group 17 element and therefore has 7 valence electrons. That's something that I've already mentioned several times in this video. And so what happens here is in step 2, you can see that any unpaired electrons get matched up. And so now they are a shared pair. All right, so this is the shared pair. These other pairs are not being shared. So these ones right here are all just going to stay the same because they're not being shared. And so when we have a shared pair of electrons, though, remember that we draw that as a single line, and you can see that single line right here. And again, a single line actually represents 2 electrons. So if we were to add these all up, bromine on the left now has 2 up here, 2 over here, 2 on the bottom, and 2 from the sharing for a total of 8. And same thing with this bromine, 2 on top, 2 on the right, 2 on the bottom, and it also has these 2 electrons shared in the middle, so that also adds up to 8 on the right. And so now they have full octets, and now they're happy. That is the whole point of a non-polar covalent bond, okay? So this is a group 17 example. So if you have another atom in group 17, this is going to be your model. So you would literally make yours look just like this, just with your abbreviation. Instead of Br, you would use what your element was. So if you have fluorine or chlorine, fluorine you would put an F, chlorine you would put a Cl. Now if you have a group 16, I have a group 16 example right here on slide 24. So here's a group 16 example right here. Instead of X's, you would go ahead and just include what yours is. So that would be either oxygen or sulfur. So taking a look here, in this case, they actually share 2 pairs. So these 2 pair up, and then these 2 pair up. And again, each pair counts as a single line, right? So this counts as 2 electrons. This one right here counts as 2 electrons. They also have 2 on the top, 2 on the left. And so together, that makes a total of 8 for this element. On the right, we've got 2 on the top, 2 on the right, and it also gets the ones in the middle, so that counts as 8 for this one. So 2 plus 2 plus 2 plus 2 for a total of 8. It is happy. All right. So again, this is if you have a group 16 element, so oxygen or sulfur. And if you have group 15, I have an example right here for you that, again, you can just copy, just replace the Y's with your element. So group 15 will be if you chose nitrogen or phosphorus. So taking a look here at nitrogen and phosphorus, you would replace the Y, for examples, with N's, or the Y's with P's. Okay, in this instance, they have 3 pairs that get shared. So these ones on top, these ones in the center, these ones on the bottom. Remember, the ones on the left and right aren't being shared, so they can stay how they are. And remember that each of these lines counts as 2. So here's 2, and here's 2. And this one on the left counts as 2, so adding those up together, that equals 8 for this element. This one has 2 on the right, and again, it also gets the stuff in the middle, so that also counts as 8 for this one. And that is happy. Again, sharing is caring. Oops, sorry, sharing is caring. That is the whole point of covalent bonds. Okay, so again, the answers are already here for you on slide 23 and 24. For slide 27, you just need to make sure to replace your name, right? So again, the group 17 example with bromine. With bromine, you're just going to go ahead and replace, what were the group 17 ones that I said you could do? I said you could do fluorine and chlorine, right? So right here, replace, oops, let me try that again. Replace with fluorine or chlorine. And then the group 16 example with X, which is not a real element, that's just an example, replace with oxygen or sulfur. And then group 15 example with Y, you would go ahead and replace with nitrogen or phosphorus. All right, so I already have those all for you ready to go. All right, so that's everything that you need to do for these slides up to this point. Thank you so much, and I will see you later.